Hello everyone. So, we will continue with the mechanical tests of geotextile. So, we will discuss now the trapezoidal tear strength test method. It is one of the tests to ascertain construction survivability test. So, how the total structure will survive once the geotextile are got damaged. This we can assess by getting the data from tear strength test. So, here initially a small cut is given in the sample, like to simulate that the geotextile is damaged by some sharp object or some stone. So, how is it going to survive? So, initially a small cut is given in the sample and the force required to propagate the tear in the sample, and that is measured. So, the force is measured, the force is applied in the sample in such a way that the initial tear is opened up. So, direction of force is such that whatever initial tear was incorporated, that will be opened up, and that is why we have to form a shape like trapeze. This trapezium will help in applying the force and the tear will start propagating. The tear strength result is expressed in terms of Newton, and which is important when the geotextile is damaged. So, in normal condition the tear strength is not that important, but in case of damaged geotextile, and if we have to use this geotextile, we cannot replace the geotextiles. So, for that how will it survive? So, that will be assessed by trapezoidal tear strength. So, this is the specimen where length of the specimen is 200 millimeter by 25 millimeter, and effective length is 25 millimeter and width is 200 millimeter, where at the midpoint a cut of 15 millimeter is imparted, and this trapezium shape helps in propagation of the cut, and the grip point is shown by the dotted line. Now, I will show here, this is the specimen, where I have incorporated one cut at the center. Now, grip will be at this point, and as the this is the like in tensile tester we will put this, and then if we test the this tear will get propagated. So, due to this shape, the trapezium shape, this tear initial cut will start propagating, and the rate of test is 300 millimeter per minute. After that, another important test is that seam strength of geotextile. normal size of roll is typically the width is 3 to 5 meter and length is 100 meter, but if we actually use in geotextile construction purpose, where we like a road construction, the width is much more than this and length obviously is not enough. So, we have to stitch, and the seam strength is important. So, larger size areas covered by the seaming of geotextiles. So, we have to stitch the geotextiles, and the thread while using the stitching, the thread should be same as the base material for geotextile. Like if it is polyester geotextile, then we have to use polyester thread. If it is polypropylene, then it should be polypropylene. The stitches are of different types depending on the application, like single stitch, double stitch, J seam, butterfly seam, as per the specification we have to use. And after forming the stitch, after imparting the stitch, we have to test the seam strength by testing the tensile strength at the stitched portion, and then we have to compare with the strength of virgin material, and the tensile strength is normal tensile strength. So, seam efficiency in percent is expressed as strength at the seam portion by strength of virgin material multiplied by 100. Now, these are the different types of seam. This is butterfly seam, J seam and flat or prayer seam type. So, these are the different types of seams, and the seam efficiency is the strength at the seam portion and strength of the geotextile without seam portion, normal tensile strength. After that, now we will discuss the compressibility testing. Compressibility indicates the reduction in thickness under applied pressure. So, it is very important for geotextile as far as the water transmission is concerned, transmissivity or permeability is concerned. If the geotextile is highly compressible, once we apply load, the pores of the geotextile will get compressed. So, its transmission characteristics will be affected. The compressibility of geotextile depends on the thickness and mass per unit area. As the pressure increases, the thickness of non-woven needle punched and resin bonded geotextile get reduced significantly, and as I have already mentioned, the transmissivity of these geotextiles gets affected. Permeability properties are dependent on the normal pressure. Compressibility of woven and non-woven heat bonded geotextiles are lower than that of needle punched geotextiles. Compressibility of non-woven needle punched geotextiles plays a very important role, as most of the time we use this type of geotextiles to pass the liquid along their plane, that is drainage characteristics. If the geotextile is highly compressible, then the drainage characteristics will get affected. this is the typical graphs of applied pressure and geotextile thickness compressional characteristics. So, this one top one is showing that non-woven needle punched geotextiles, which is heavier geotextile, and non-woven needle punched lighter geotextile. So, needle punch geotextile which we have seen here, it is actually showing very high compressibility, whereas non-woven slit film is having least compressibility. Next characteristics is that puncture resistance. This is extremely important because in application the geotextile material sometimes comes across the pointed stones or any other objects which will ultimately result punching of the geotextile, and this initial damage will deteriorate the characteristics. It will gradually, it may result larger holes and effectivity of the geotextile will be lost. So, here it is tested by 8 millimeter diameter probe. This is 8 millimeter diameter probe which is punched into a stretched geotextile material. This is geotextile, stretched geotextile, where this container diameter is 4.5 centimeter, 45 millimeter diameter, and here peak load is measured just before the punching is occurred. Another method of punching test is severe puncture test, that is California bearing ratio puncture test. This California bearing ratio test is basically it is used to test the compressibility of soil particle, but the same method we can use here. Here the probe is of 50 millimeter diameter, this is 50 millimeter diameter probe, and the container is 150 millimeter diameter, this container is 150 millimeter diameter. Normally in this container when we test the severe test, we fill this container with the soil, but here it is modified where we are holding the geotextiles. 10 specimens across the roll width will be tested, strength and deformation is monitored. So, both the strength and the deformation, that is the penetration will be monitored and average value is reported. Now, let us see how this severe test gives idea about the elongation and the tensile strength of geotextiles. So, from the severe value we can calculate the wide width tensile strength, that is TF, tensile force kilonewton per meter. Fp is the punching force, that is the punching force, downward punching force Fp, which is in terms of kilonewton, and R, if R is the radius of the severe plunger, then the circumference will be, total circumference will be 2 pi r. So, Fp by 2 pi r is actually tensile strength of the geotextiles. So, from severe test we can measure the tensile strength of geotextile, as well as we can measure the strain at failure, strain percent. Initial length is the difference between the diameter of the plunger and the base material. X is the horizontal distance between outer edge of the plunger and the inner edge of the mold, this is the distance here, and when the plunger is moving down, the length A has been extended to x. That means, the strain percent is x minus a divided by initial length a. So, if we express in terms of percent, then it will be strain percent. So, from CBR test we can measure the tensile strength and tensile elongation. Now, let us see what is actual CBR test, California bearing ratio test. In this test, that CBR is a penetration test for evaluation of mechanical strength of road subgrade, that is soil or any subgrade material, and base course. So, low road subgrade and base course we can measure the mechanical strength. It was developed by California Department of Transportation, that is why it is known as California bearing ratio test. The test is performed by measuring the pressure required to penetrate a soil sample with a plunger of standard area. So, standard area plunger is there. Now, pressure required to penetrate a specific distance. The measured pressure is divided by the pressure required to achieve an equal penetration on a standard crust rock material, that is a standard crust rock material. So, we need to have a specified penetration, and then we compare the pressure required for that penetration. Now, here this is a soil sample and plunger is there, okay, standard and applied pressure, and here we can measure the penetration by transducer, and we can have two types. One is a cylindrical type plunger, or we can alternatively we can have annular weight also. This annular weight we can use. This is sample standard mold. The steps are the take load readings at penetration of all these values. So, 0.025 inch, 0.05 inch, 0.1 inch, 0.2 inch, 0.4 inch, at all these penetration values we take the pressure requirement, say 70 psi, 115 psi, 220 psi for 0.1 inch, for 0.2 inch 300 psi, 0.4 inch 320 psi. So, we record all this standard pressure value and for a particular penetration, and this is the reading for a particular soil. Now, we have to calculate the CBR value of this soil. To calculate the CBR value, we need to know the force or pressure required for a particular penetration of standard sample. The standard specimen values are given. These are the penetration versus load required or pressure required. Now, the gold standard values of CBR, these are the standard value is for 0.1 inch of penetration, the standard crust California limestone has got 1000 psi value. This is the standard value. For 0.2 inch penetration, it is a 1500 psi, okay, and this we have to compare with the existing sample. For our present sample, the value for 0.1 inch was 220 psi, for 1.1 inch 220 psi here, for 0.2 inch it is a 300 psi. Now, if we take the ratio, that will be California bearing ratio. Now, here CBR value is the test example psi, that is whatever our specimen PSI and standard PSI, that is CBR value. So, in our case for 0.1 inch penetration it was 220, if we divide by 1000 which is standard, it is coming out to be 0.22, say 22% CBR value, and 0.2 inch penetration it is 20%. Normally what we do between 0.1 inch and 0.2 inch penetration, the CBR value which is higher we used to take here. So, here for 0.1 inch it is 22%. So, effective CBR value for the soil is 22%. Now, the CBR is that in general the harder the surface, higher is the CBR value. A CBR of 3 means it is a very low, it is a tilled farmland. CBR 4.5 it is a moist clay, moist sand will have around 10 value CBR, high quality crust rock it will have 80, and standard crust California limestone will have 100, because it is a ratio with respect to that value. So, depending on this CBR value we have to select the geotextile. Next mechanical characteristics is that dynamic puncture strength. We have discussed the punching strength for composite also, but for geotextiles the test method is little bit different. Here 1 kg pointed cone of standard dimension is dropped from a height of 1 meter onto the stretched geotextile specimen. So, here it is a ring, the geotextile specimen is stretched, and after dropping we calculate the diameter of hole made by the cone. So, this cone is graduated. Okay. Here we can get the diameter value directly, the larger the hole diameter lower is the puncture strength. So, this will give an idea about the effectivity of the geotextile during its application. Next characteristics is bursting strength. Burst strength, there are 3 different types of burst strength. One is Mullen burst strength, where inflated rubber is used, which is normally we use for textile material. Ball bursting strength we normally use for highly stretchable textile material, and third method is again here we can use severe burst strength. So, the analytical analysis of burst strength test is that the burst strength is required to design the geotextile for specific separation. So, here the its geotextile is used for separation purpose, and when the soft soil is pumped inside the stones, when the stone is applying pressure downward, the soft soil will try to pump up and it will simulate the bursting condition. The geotextile may burst due to the applied upward load. So, due to the upward load, this is the field model for burst resistance test, and theoretically from the field concept the Giroud again developed empirical formula to calculate the required geotextile burst strength T required. So, what is T required? It is half Pg multiplied by dV multiplied by elongation. So, what is Pg? It is the pressure exerted upward, and dV is the diameter of the void, and this is elongation. Elongation can be calculated using this formula. So, elongation equal to 1/4 multiplied by 2 ZV, where ZV is the deformation of the void and WV is the width of the void. So, from this formula we can calculate the elongation strain of the geotextiles. So, it can be analogous to the field condition like stone punching into the separation layer. So, this can also be the condition, not only the soft soil is pumping up, this can also be the condition. So, inflatable rubber membrane is used to distort the geotextile into a hemispherical shape of diameter 30 millimeter. This is a 30 millimeter, this shape is hemispherical shape. Geotextile is pushed upward and it forms hemispherical shape, as well as the fail is due to radial tension. This fail of the geotextile, that it fails due to the radial tension. So, ultimate tensile strength, ultimate strength of geotextile we can calculate by T ultimate tensile strength, half Pb is the bursting strength, dB is the diameter of burst equipment, that is the 30 millimeter, and epsilon g is the strain of geotextile. If we know the strain, diameter of burst equipment and pressure required to burst, we can calculate the tensile strength of the geotextile. So, using this formula we can calculate the factor of safety also. So, allowable tensile strength is equal to ultimate strength by cumulative reduction factor CRF. So, this ultimate tensile strength, as we have seen here, we can, if we replace, we will get the factor of safety, allowable tensile strength by required tensile strength. So, we will get the factor of safety is equal to Pb multiplied by dB divided by CRF Pg by multiplied by dV. Here void diameter, as we have seen, is 0.33 to that of average diameter of the stone, dB is given 30 millimeter and CRF if it is 1.5. So, we can calculate the factor of safety. So, from this equation we can calculate the required factor of safety of geotextiles. The next characteristic is the properties which influence the soil geotextile interaction. So, mainly it is a mechanical interaction. Here we will discuss the frictional characteristics between soil and geotextiles. So, it is characterized by the shear strength developed between soil and geotextile. Suppose a soil structure is trying to slide or geotextile is trying to slide over the soil structure. So, how much friction is there between the soil and the geotextile? So, we can assess by these methods. To reinforce with soil, high contact shear strength is required. So, for reinforcing purpose, we do not expect that there will be sliding between soil surface and the geotextile surface, whereas low contact shear strength is required when soil and geotextiles are designed to move against each other. So, depending on the requirement, we can select the particular geotextile for particular soil. Shear strength is governed by the angle of interaction, that is angle of friction developed between soil and geotextile, and this interaction we can evaluate by two methods. One is pull out test, another is direct shear test. Here it is a pull out test. This is same as that we have discussed in composite, the single fiber pull out test. The concept is same here. Here the geotextile sample, the specimen is confined between the soil surface, and at the end the geotextile is clamped and then it is pulled out, and the pulling force is recorded. Higher the pulling force means higher will be the interaction, and we apply the normal load which is constant. Another method is that here this is one soil surface which is covered with geotextile specimen, and at the top box which is filled with soil and normal pressure is applied, and then this top box is actually pulled, it is sheared against the geotextiles, and this pulling force is measured, and depending on the frictional interaction between the soil and the geotextile, this pulling force will change, and we can evaluate the interaction force. Now, we will start discussing the hydraulic properties of geotextiles. First, we will discuss that apparent opening size. For any hydraulic characteristics, means the flow characteristics of water mainly through geotextile depends on the pore structure of geotextiles, and the combination of pore structure and soil particle size, it is important for proper designing of geotextile for their particular hydraulic characteristics. So, to get effective hydraulic properties, we have to select geotextiles, we have to understand, we have to know the opening size of geotextile and the relation between the opening size and the soil diameter is extremely important. So, in hydraulic properties we will discuss how to measure the apparent opening size, then we will discuss cross plane permeability, in plane permeability, long term permeability, and then finally we will discuss gradient ratio test. First, apparent opening size. As per ASTM method, which is called dry sieving method, where the glass beads are used and these glass beads are uniform in size. So, the test method involves in sieving uniform size glass beads through the geotextiles, and main advantage is that the method is relatively faster compared to any other method. So, faster and simple method. Here we take 50 gram of smallest beads available. So, typically 75 micron beads, and which is sieved them for 10 minutes. So, sieving is there for 10 minutes, and then we have to determine the percent of glass beads retained on the geotextiles, and this same process is repeated with higher size of the glass bead till the required percent of glass beads passing through, which is x percent, is achieved. Now, a graph is drawn between the glass bead size on x axis and percent passing in y axis. And how do we express the result? If we know the percent passing, then we can calculate the percent retained. So, let us see, if y percent of the certain particle is retained on geotextile, then OY of the geotextile is the size of the particle in millimeter, using usually 90% and 95% are used. So, OY means that y percent of that particle size is retained. What does it mean? As per ASTM, that AOS, apparent opening size, is expressed in either O95 or O90. So, as per ASTM, its O95 corresponds that 95% of particles are retained. That means 5% particles are passing through the geotextiles, which means 95% of pores are smaller than that specified size of particle. So, 95% O95 means that 95% of the pores are smaller than that size. Now, let us see how to measure. These are the sieves available. Now, this is the instrument here, and this curve shows we start with the smallest particle size. This is the smallest particle size, say 75 micron, and we start sieving. And when we have observed here that typically around say 12% particles are, this is finer particle, these are 12% particles are passing through. Here 10% particles are passing through, that means 90% particles are retained here with this size, and at this point it is showing that 5% particles are passing through, that means 95% particles are retained if the particle size is this one. That means here it is 150 micron. 150 micron means, that means 10% of the particles will be passing through the geotextiles, 90% of the particles will be retained here. So, the apparent opening size of the geotextile O95 equal to 150 micron. What does it mean? O90 150 micron means the 90% of the pores are less than 150 micron. Similarly, O95 230 micron means 95% of the pores are less than 230 micron. That is the significance of apparent opening size. So, what are the limitations of this method? The method is actually cannot be used for very thick nonwovens, because that may entrap the glass beads within the structure. For geotextile of oven structure, yarn in some geotextiles like oven geotextile may move during testing, during sieving, that may affect the apparent opening size method. Glass beads may simply float instead of going through the geotextile because of their low mass, because lighter glass beads while sieving they may simply float on the geotextile, and most important drawback is that the electrostatic charge may be developed. It may generate, and which will affect the free flow of the particles through the pores. So, in that case, to avoid this problem, antistatic spray can be applied. Another method which is similar to dry sieving method, which is called hydrodynamic test method for AOS, apparent opening size, which is called as wet sieving method. The test methods are exactly same to that of dry sieving method. Uniform size sand particles are used here instead of glass beads. Geotextile with sand particles is repeatedly dipped into the water and taken off instead of normal sideways sieving. Here we test the repeated dipping and taking out. Percent of sand particles passing through the geotextile is determined after each test. Procedure of test is similar to the dry sieving, as we have seen using glass beads. This process overcomes many limitations of dry sieving, like generation of static electricity or floating of glass beads. In some cases, well graded sand is washed down by water and soil particle is collected below. The geotextile are also analyzed. So, that will show the piping characteristics of geotextiles. So, how the soil particle is lost, what is the quantity, what type of soil, that also be analyzed here, in addition to the apparent opening size measurement. This is the method here, and here it is a geotextile sample, and we place some sand particle here, and the total mold is dipped and taken out, and the amount of sand particle retained is measured. Based on the apparent opening size and the size of the particle, we can design the filter. There are different filter criteria. So, fine soil particles should not be lost, that is the first criteria of geotextiles, although the pore sizes are more than the finest particle. Pore opening should be large enough for the proper water flow. So, there should be proper flow of water, for that pore size should be large enough. So, there are two criteria, one is piping limit, that means the soil loss should not be there through geotextile. For that O90 should be less than equal to D85. O90 is the apparent opening size of 90%, that means 90% of the particles, 90% of the pore sizes are less than that size. D85 means 85% of the particles are of diameter less than that particular size. So, for piping limit this is the condition, and for permeability limit the condition is this, O90 should be more than equal to D15 of soil. So, O95 means the characteristics of geotextiles, D15 is the characteristics of soil particle. So, for permeability we should have minimum opening size, and for piping we should have minimum diameter of soil. Now, here for selection of pore size, where hydraulic conditions are less demanding, that means the waves are not there, the pressure is not very high, there is no turbulence, the flow of water is streamlined. So, not demanding condition, the diameter of largest textile holes, that means largest diameter, that can be up to 5 times larger than that of largest soil particle, which is very important. Let us try to see, understand. So, apparently it looks, this is the largest size, that means O95, O90, and here the diameter is the D90. As per this condition, D90 is 5 times to that of O90. So, that means opening size is larger than the particle size, which means the particle will simply flow through these pores, but it is not the actual case. Initially there will be definitely little bit piping, but after certain time these particles will form a structure, and initially there will be larger size particles and gradually it will form a permanent structure, and as the hydraulic condition is not demanding, so the water will flow through these pores created by the soil itself without losing the soil. So, this is the stabilized condition. and under difficult hydraulic condition where there is a turbulence, okay, the waves are there, in that case O 90 equal to D 90. Particularly difficult hydraulic conditions exist in soil when under wave attack is there, where the soil is loosely packed, low bulk density, where the soil is of uniform particle size, or where the hydraulic gradients are high. So, in all these conditions we have to select the criteria O 90 equal to D 90. Now, we will discuss the test method for cross plane permeability. So, there are different types of test. One is constant head test, there are other tests like falling head test. In constant head test, 50 millimeter constant head difference between upper and lower surface of geotextiles are maintained. Water is allowed to flow through the opening of 25 millimeter diameter. Volume flow is given per unit time. So, that is the volume in liter per second, okay, that is called volume flow. Temperature correction is needed to be applied finally if the temperature changes. So, we can apply some correction. So, I is the gradient which is water head divided by thickness, that means the distance travelled through the geotextile as it is cross plane. So, here distance is thickness, and using this formula we can calculate the flow rate. So, flow rate equal to Kn I A, where Kn is permeability coefficient in meter per second, okay, I is a gradient and A is the area of flow, and I is nothing but water head delta H by thickness T, and Kn we can calculate, and psi is a permittivity. So, we can calculate using all this formula, and this is the setup for measuring the cross plane permeability. Manometers are used to measure the water head, okay, and this is water column, geotextile sample, and here it is a water outlet, and we can measure the volume of water passing through geotextile per unit time. So, we will now see the numerical how do we measure the permeability coefficient or permittivity with a given data. So, this data from a test of cross plane permeability is given below. Estimate the permeability coefficient and the permittivity. So, 500 milliliter of water collected in 300 seconds under 50 millimeter head of water. Thickness of geotextile is given as 0.65 millimeter, diameter of opening of permeability device is 25 millimeter. So, flow rate can be calculated, 500 by 300 is 1.67 milliliter per second, or we can convert it to cubic meter per second. Area we can calculate by knowing the diameter of the opening, that water head is 50 millimeter, that is 0.05 meter. From there we can calculate the permeability coefficient, and it is coming out to be 4.42 multiplied by 10 to the power minus 5 meter per second, and permittivity is 0.068 per second. So, we can calculate all this parameter from a set of given data. So, we will stop here, we will continue with other methods of measurements of hydraulic characteristics. Till then, thank you.